Thank you all. I'm Frank Nothaft. I'm from UC Berkeley, and in case you're kind of worried about work coming from UC Berkeley after our keynote earlier this morning, I'm glad to say that a lot of our collaborators on this project are based on the East Coast. So, yeah, I'll be talking today about Atom. So Atom's a distributed computing environment for working on genomic data. What is in Atom? So Atom is part of a bigger project called Big Data Genomics. We have really two core projects. We have Atom, which is the core API. So we provide a lot of, what we think of as, not, I guess maybe canonical transformations and ways of doing joins with regions and other data. So ways of processing genomic data at scale. We also have BDG formats, which is a data schema. So we provide schemas for expressing reads, variant calls, assembly contigs, genome annotations. On top of this, we've been building a lot of tools recently. So I've been working on a tool called Avocado, which is a distributed local assembler. So this is a variant calling tool similar to the haplotype caller in the GATK. Yesterday at the hackathon, we were working on RNA Atom, which is just an RNA analysis package for built on top of Atom. So yesterday we were working on a distributed implementation of the defuse algorithm for calling fusion transcripts. Some of our colleagues at the Genome Bridge have been really pushing hard on this BDG services project. So this is a way to easily spin up and send jobs to a cluster that is running Atom. So you don't have to have it kind of simplifies some of the access control and management of data for a large shared data repository. Additionally, we're working a bit on de novo assembly on a distributed setup, and then finally the team at Mount Sinai has been really pushing hard on semantic variant calling. So they have this semantic variant caller that implements algorithms similar to VARScan or Mutect. They're able to process through a tumor normal pair in about 20 minutes. So they're pretty excited about that, and they're competing this in the Dream Challenge. We have several big design goals for our platform. Our real interest is to develop a processing pipeline that allows efficient, scalable use of clusters and clouds. So we've built our system on top of Apache Spark, which is an in-memory MapReduce system that provides a clean, simple, functional API for expressing data translations, and unlike Hadoop, allows you to very efficiently do iterative computation. So a lot of the computation in genomics is iterative. You have some processing step followed by another processing step, and then maybe you try to infer something from the data. So this allows us to really efficiently run long genomic pipelines. Additionally, we're trying to make a lot of changes at the data format level. A lot of people are familiar, with BAM, SAM, CRAM, other formats. These formats are, they're hard to split up between many machines, and they run into some cross-compatibility problems. So we've actually gone ahead and we've shifted from having a file format as a definition to defining all our data storage with a schema. So this allows us to flexibly move our data between a database or some very efficient underlying file format. Without having to do a lot of interoperability work. This essentially is a way to abstract the way that we represent data from the way that we store data. And from this, in our kind of production pipeline, we have a fast file format called Parquet that we use to store data. And I'll talk about this a bit more in a second. From the implementation side of the project's all written in Scala. That's the language that Spark uses to expose its API. It's about 27,000 lines of code. All of our code is Apache licensed. So we're all open source on the Apache 2 license. We have 21 contributors to the project, spanning across 8 institutions. And we're, for the core pipeline, the core aligned reads to variant calling pipeline, we're hoping to have what we would call production quality release available sometime in the end of this year. One of the, as I mentioned earlier, one of the big things that our design principles is to have a well-decomposed software stack. inside of Apache Spark, the general abstraction that you get is this thing called a RDD, or a resilient distributed data set. What this essentially looks like is a large array that is spread across many computers. So what we've implemented in Atom is really this API and command line that does the operations and the translations at this level. So we really expose a big distributed array of reads or variant calls to you. The advantage of this is that then this gives us a lot of ability in the implementation level, below the API, to optimize how we store data, how we interchange data, and what we're running on. So, for example, by default in Spark we use HDFS, the Hadoop distributed file system. But one of the big things that we've been working on in this BDG services project is the ability to, instead of using HDFS, is to store your data in S3 or in some other cloud store. So this is really useful if you have a lot of data that's sitting in S3. For example, you want to access the thousands genomes BAM files that AWS hosts. There you don't have to pull the data over locally, then copy it into HDFS, then run. Instead, you can just pull directly from S3, and this gives you, this is a nice performance optimization. It saves you a second copy. And additionally, once again, since we're storing all our data with the schema format, we don't have to worry, we don't have to expose how data is stored on disk to someone who's programming at the API level. So that allows us the ability to, to really translate formats on disk on the fly. So for example, if you do want to operate on, on VCFs or on BAM or SAM files, we do a lot of interop through calling out to the Hadoop BAM library. If you have data that's stored in the native Atom format, we just store it in this Parquet columnar database, and we get very high read throughput. So this is just kind of another summary. The big principle that we have is that we want to expose these rich and scalable APIs, and we want to play nicely with other tools. So we've really been focusing on this interop layer recently. One of the things that's very cool, we have a pilot project going with some researchers from Microsoft Research, where we're actually using Atom for some of the pre-processing stages, and then when we have this large cluster of 10, 20, 100 nodes, we're actually calling out to Freebase as a variant caller. They have some people who are really interested in Freebase. They like the algorithm. So even though we're running inside of Atom, we can natively call out to a tool that doesn't yet support the Atom format. And then once that finishes running, we're still back in the Atom format. It's very scalable, and we can run further analysis on the data there. So this is, that's a big focus for us, not, kind of trying to be democratic about, how the data is stored, not try to force anybody into our system. One of the things that I'll talk about today is the way that we're storing our data. So I mentioned earlier that we use Parquet. So Parquet is an open source columnar data format that was created originally by Twitter and Cloudera, and it's based upon Google Dremel, which is a high performance columnar data store that was published a few years ago by Google. And this is an Apache license project. It actually just entered the Apache incubator last month. So there's a few advantages to this file format. So the big thing is that it's columnar. So instead of storing all of our records, instead of having a row-oriented column where we write, a single BAM record followed by another BAM record followed by another BAM record, we would actually store all of, the sequences in one column, then all of the quality scores in another, all the read names in another column. This allows us to independently access the columns, and we can also do a lot of efficient, things to compress data. For example, in BAM files, you have this, this header that stores a lot of the metadata, like the read groups and how the reads were actually run through the sequencing information, or sorry, the sequencing system. In BAM, you actually have to store this in a header, and then if you want to access this data, you have to go globally pull it out. In Atom, we're actually able to store in this columnar format. It compresses down really well because when Parquet is writing or reading the files, it says this is a value, there's like, maybe we have 16 read groups, so we have 16 values in this column even though we have 750 million records. So it only stores, the highly repeated elements, it just greatly compresses them down via a dictionary. So we're actually able to get about depending on the exact file, we're somewhere between 5 and 25% smaller than BAM files without doing any sort of lossy compression or really any big tricks. And additionally, we get very fast scans because we only load the columns that we need. And then additionally, Parquet actually parallelizes all of the columns out into different files and into different read groups. So we're able to read many different of these read groups in parallel. Now kind of talking more from the algorithmic side, one of the big algorithms that we've been looking at is base quality score recalibration, which is featured prominently in the GATK. This is a pretty slow algorithm in the GATK. I think right now they say for a whole genome it takes about 17 hours to do. However, it turns out that this is a very, very easy algorithm to parallelize. If you're not familiar with the algorithm, essentially what you're doing is you're dividing bases up and you're putting them into buckets based on shared covariates. So for example, I put all of the bases that are in read group 1 into one bucket, and then I put them into further buckets based on what the quality score that the actual sequencer gave me was. Once I have those there, I look to see, did this base differ from the reference at that site? If so, it was probably an error. If not, it was probably correctly observed. I recalculate my quality scores, and then I update the quality scores of all of the bases that were in that bucket. When we use it on top of Spark, all of these calculations are done in parallel. So each one of these buckets is computed on in parallel. The only big thing that we have to do serially is that we have this table of variants that we broadcast out that we use to mask. So for example, if we have a variant, or if we have a mismatch at a site that is a variant that we see in dbSNP, that could actually very well be a true variant, not just an incorrect observation. So we mask out that site and don't count that against us when we're recalibrating. So what we do is we broadcast that table out. We map all the reads down to the bases. We put all the bases in the buckets, so that's a parallel aggregation. We calculate the empirical values, and then we just broadcast that observation back out, and then finally apply that to the reads, all in parallel. So the big thing with this system is that we get very great performance and scalability. So for example, if you compare our performance to Picard, we're actually about 2x faster when we're running on a single node. And once we move to a large cluster on EC2, we're able to get about a 50x performance even using smaller machines. Additionally, we've been really working on concordance with existing tool flows. So for the GATK BQSR algorithm right now, we have about 99% concordance, and we've traced down the 1% of discordant calibrations to an error in the GATK. Similarly, we're fully concordant with Picard for marking duplicate reads, and we have the additional ability to actually mark chimeric read pair alignments that is not supported in Picard. So in terms of future work, we're really pushing hard towards a production release, and we're working hard to build this complete analysis pipeline, as shown by the many tools that we're working on, and trying to build out more algorithms. Otherwise, we're very interested in building out Python bindings. Python's a very popular language in bioinformatics, and we've had several people who've asked us to do this recently. Spark itself has Python bindings, and the Avro data schema that we use also binds to Python. So that's an area of work for us. And then finally, we're working on global interoperability as well as interoperability with the Global Alliance for Genomic Health API. Finally, we're an open source project. That's why we're here. We're always looking for new contributors. We've had 3 contributors join in the last 2 weeks. If you're interested, we maintain a list of open enhancements at our GitHub. Our GitHub's right here. And finally, we're also looking to hire 2 full-time engineers at UC Berkeley to support this work. So if you're interested, please come up talk to me, be glad to put you in touch with the people who are doing the hiring. Finally, I'd just like to acknowledge all of our contributors. We were lucky we had both people from the Genome Bridge and Michael here today. We're really glad that we have such a large community that's started to work on this project, and just wanted to acknowledge the funding support that we get at Berkeley. Thank you very much.
So any questions? If you can, please come up to the mic to ask questions. So one thing I wanted to ask is, so sure. you looked at Parquet. Have you looked at other compressed data formats? I know HDF5 has been mentioned a few times as a nice format, but...
we haven't looked too much at other compressed formats, mostly because Parquet is giving us pretty good compression, as well as very high read and write throughput. So for our current applications, that's sufficient. If we wind up being more concerned about data storage and compression level, we'll probably look at those a bit further. Just right now, Parquet is a very good knee in the curve for us.
Okay, very good. Anybody else? All right. With